Black holes are weird. Like really weird. Imagine a place in space where gravity is so strong, nothing can escape. Not even light. That's a black hole. These cosmic objects are like giant vacuum cleaners, sucking up anything that gets too close. But instead of dust bunnies, they feast on stars, gas, and even other black holes. Black holes are invisible to our telescopes because they don't emit light. But we know they exist because of their effect on nearby stars and matter. So, how do these bizarre objects form? Hold on to your hats, because we're about to dive into the wild world of stellar evolution. Stars, like our Sun, aren't just scattered randomly throughout the universe. They are born in massive clouds of gas and dust called nebulae. These nebulae, often referred to as stellar nurseries, are the birthplaces of stars. Gravity plays a crucial role in this process. As gravity pulls the gas and dust together within a nebula, the cloud collapses. This collapse causes the material at the center to heat up. Eventually, the temperature and pressure at the core becomes so intense that nuclear fusion ignites, marking the birth of a star. Once a star ignites, it enters a long period of stability, fusing hydrogen into helium in its core and radiating energy into space. Our Sun is currently in this stage. However, this stability doesn't last forever. Eventually, a star will run out of hydrogen fuel in its core. What happens next depends on the star's mass. Smaller stars, like our Sun, will expand into red giants and eventually shed their outer layers, leaving behind a dense core called a white dwarf. Massive stars, however, are destined for a more dramatic fate. They will undergo a series of nuclear reactions, fusing heavier and heavier elements in their cores. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses in on itself, triggering a catastrophic explosion called a supernova. If the core of the star is massive enough, at least 3 times the mass of our Sun, the gravitational collapse continues unabated. Nothing can stop the core from collapsing into an infinitely small and dense point called a singularity. This singularity is the heart of a black hole. The intense gravity of the singularity warps the fabric of space-time around it, creating a region from which nothing, not even light, can escape. Section 5. Stellar mass versus supermassive. Different types of black holes. Black holes come in different sizes. Stellar mass black holes, like the ones formed from supernovae, are typically a few times more massive than our Sun. However, there are also supermassive black holes, millions or even billions of times more massive than our Sun, lurking at the centers of most galaxies. How these supermassive black holes form is still a mystery. One theory suggests they grow by consuming stars and gas clouds over billions of years. Understanding the formation and evolution of supermassive black holes is one of the biggest challenges in astrophysics today. Section 6. Event horizon, the point of no return. Imagine a sphere surrounding a black hole. This sphere marks the boundary beyond which the gravitational pull is so strong that escape becomes impossible. This boundary is called the event horizon. Once something crosses the event horizon, it's gone forever, at least from the perspective of an outside observer. The event horizon is not a physical barrier. It's simply the point of no return, the point where gravity wins the ultimate battle against light and matter. Scientists believe that the event horizon holds clues about the nature of gravity and the fundamental laws of physics. Section 7. Spaghettification. What happens when you fall into a black hole? Let's say you were brave, or maybe foolish enough, to take a trip into a black hole. Imagine the thrill and the fear as you approach this mysterious cosmic entity. What would happen to you? Would you find another universe, or perhaps a gateway to another dimension? Well, it wouldn't be pretty. The reality is far more terrifying than any science fiction story. As you approach the black hole, you would experience extreme tidal forces. These forces are due to the immense gravitational pull of the black hole. These forces would stretch your body out in a process known as spaghettification. It's a rather gruesome term, but it accurately describes what happens. Your feet, being closer to the black hole, would experience a much stronger gravitational pull than your head. This difference in gravitational force is what causes the stretching. This difference in gravity would stretch you out like spaghetti. Imagine being pulled apart, your body elongating more and more as you get closer. As you fall further into the black hole, the tidal forces would become so intense that they would rip you apart, atom by atom. Ouch! It's a slow and painful process, one that no one would want to experience. The black hole's gravity is so strong that not even light can escape it, and once you're inside, there's no way out. Section 8. Hawking radiation, black holes, aren't entirely black? Black holes are often depicted as cosmic vacuum cleaners, sucking up everything in their path. But it turns out, they might not be entirely black after all. In the 1970s, physicist Stephen Hawking proposed that black holes can actually emit radiation due to quantum mechanical effects near the event horizon. This radiation, known as Hawking radiation, is incredibly faint and difficult to detect. But if it exists, it means that black holes slowly lose mass over time. Hawking radiation is a mind-bending concept that challenges our understanding of black holes and the nature of the universe itself. Section 9. Black holes and time. The ultimate time travelers? Black holes are not only cosmic vacuum cleaners, but also potential time travelers. These mysterious objects have fascinated scientists and science fiction enthusiasts alike for decades. Einstein's theory of general relativity tells us that gravity affects time. This groundbreaking theory revolutionized our understanding of the universe and introduced the concept of spacetime. The stronger the gravity, the slower time flows. This phenomenon is known as time dilation, and it becomes extremely pronounced near massive objects like black holes. Since black holes have immense gravity, time near a black hole flows much slower than it does on Earth. Imagine spending just a few minutes near a black hole, while years could pass by on Earth. This means that if you were to observe someone falling into a black hole, you would see them slow down and eventually freeze at the event horizon, never actually crossing it. This is due to the extreme time dilation at the event horizon. However, from the perspective of the person falling in, time would continue to flow normally. They wouldn't notice anything unusual as they crossed the event horizon. They would cross the event horizon and eventually reach the singularity, the point of infinite density at the center of the black hole. This journey into the unknown remains one of the most intriguing mysteries in astrophysics. Could black holes be the ultimate time machines? While we don't have the technology to explore them yet, the possibilities they present continue to captivate our imagination and drive scientific inquiry. Section 10. Mysteries of the universe, what we still don't know. The universe is vast and filled with wonders that continue to baffle and amaze us. Despite our advancements in technology and science, there are still countless questions that remain unanswered. Black holes are some of the most mysterious and fascinating objects in the universe. These enigmatic entities, with their immense gravitational pull, have intrigued scientists and astronomers for decades. They challenge our understanding of gravity, space-time, and the very nature of reality. Einstein's theory of general relativity provides a framework, but black holes push the boundaries of this theory to its limits. While we have learned a great deal about black holes in recent decades, many questions remain unanswered. Researchers around the world are tirelessly working to decode the mysteries that these cosmic giants hold. What happens to information that falls into a black hole? This question, known as the information paradox, has puzzled scientists for years. Does the information get destroyed, or is it somehow preserved? What lies at the singularity? The core of a black hole, where density becomes infinite and the laws of physics as we know them break down, remains one of the greatest enigmas in astrophysics. Can black holes be used as portals to other universes? The idea of black holes as gateways to other dimensions or parallel universes is a tantalizing concept that has captured the imagination of both scientists and science fiction enthusiasts alike. These are just a few of the mysteries that continue to intrigue and inspire scientists today. The quest to understand black holes is not just about solving puzzles, it's about expanding our knowledge of the universe and our place within it. As we continue to explore the universe and push the boundaries of our knowledge, black holes will undoubtedly continue to captivate our imagination and fuel our quest to unravel the secrets of the cosmos. With each discovery, we move one step closer to understanding the profound mysteries of the universe.